Hi, welcome to the first module of Lecture 12. This is the third lecture in the part corresponding to linear algebra and deals with some more advanced topics related to linear algebra. Now, by advanced topics, I don't mean something that's like way out there. This is stuff that is used regularly in political science. However, it's not stuff that you often see in your first year's classes necessarily, and therefore this is a lecture that you can in theory skip for now if you're looking just to get ready for your first year's classes and don't want to immediately immerse yourself into all the ways in which linear algebra might be used as you go forward. That said, this is stuff that is used very frequently in political science and all the social sciences, and therefore is stuff you should eventually look at, even if you put it off now before your first year's classes. Okay, so we're going to cover two major topics in this lecture. The first is eigenvalues and eigenvectors. The second is Markov chains and stochastic processes. These are both pretty broad topics. You can take an entire class in stochastic processes. For instance, more than one class. We're going to just cover on some introductory material to get you an idea of how this stuff works, and with some examples for where it's used in the social sciences. Okay, so let's begin by talking about eigenvalues and eigenvectors. And I'm going to write those here because those are not familiar words to most people. So an eigenvector and an eigenvalue. These are corresponding terms. For every eigenvector, there's an eigenvalue and vice versa. Eigen translates roughly into characteristic. These are characteristic vectors and characteristic values of matrices. Okay. Now, to understand what the intuition is behind these things, we have to sort of imagine what matrices are used for in general. So recall that a matrix, right, can represent an operator that takes some vector into another vector. So here in general, you might have some matrix A that takes some vector x and transforms into a different vector y. Right? So this is how we dealt with matrices in the previous lecture. You had some operator A, some matrix operator that transformed a vector x into a different vector y. Okay, and I apologize for my voice here. I've been under the weather for a week or so. So this is one way of writing a matrix equation. Recall that we've done a whole bunch of stuff. We could figure out how this thing was solved. We did matrix inversion, for instance, and showed that if A were invertible, then you could write it like this, and you could solve for x that way, and so on. Right? This is a way you can write in a system of equations as this. Right? So here's one way of writing that. Now let's think about it a little more abstractly, right? And not in a scary way, just a little more abstractly. So what does this mean? Well, geometrically, you have some vector x, which is some arrow basically pointing in some dimensional space. It helps think about it in a three-dimensional space, and some arrow pointing in three-dimensional space. Then this matrix A comes along, and it transforms this vector into a different vector. Right? That might mean rotating it on a plane. That might mean flipping it around. That might mean changing it from being in the xy plane to the z direction. Whatever it is, it's some transformation of the vector x into something else. Now, what does that mean? Well, you might imagine that for any particular matrix A, it might have different effects on different vectors. Some vectors might rotate, some vectors might flip, but some vectors might end up staying along the same line. Vectors that stay along the same line that they were on in the first place, so they stay pointing either in the same direction or flip in the opposite direction, but stay on the same line, are eigenvectors of the matrix. They're characteristic vectors of the matrix, and they don't change their direction when you apply the matrix to them. So in some senses, they're very characteristic of the fundamental nature of the matrix. The matrix does not move them around. It keeps them on the same line as before. So in other words, you have some it takes some vector like this and puts them back in the same direction, although maybe extended or flipped or contracted. You can change the size of the vector and maybe the direction in terms of like forward or backward along that line, but you keep it along the line. This thing here is an eigenvalue or eigenvector equation. It specifies what the eigenvectors of the matrix are. These x's here are eigenvectors, and often you see a v used instead of an x. Obviously the same thing, doesn't matter what you call them. But this is an eigenvector equation. It's also an eigenvalue equation. This lambda here, this letter lambda, is an eigenvalue corresponding to the eigenvector v. And this equation helps you figure out how to solve it. Now we'll go through and actually see how to solve for lambdas in the next module, and then see how to solve for v's in the module after that. It's not too bad, and uses the stuff we did in the previous 2 lectures. But conceptually, this is what it means. It means you take a vector, and if it's a characteristic vector, if it's an eigenvector of the matrix, when you apply the matrix, you stay along that same line that the original vector pointed in, possibly extending it, possibly contracting it, possibly flipping its sign, but it's along that same line still. Okay, so that's the fundamental intuition behind these things. Why do we use them? Well, we use them, and again, they're defined. This is how they're defined. This is the definition of an eigenvalue and an eigenvector. This is it. Now, how are they used? Well, they're used in a lot of ways, actually. We'll discuss a whole bunch of them in the 4th module of this lecture. One way is in principal components analysis, or factor analysis, when you're trying to break down some complicated space into some dimensions of commonality between units. You end up using the same kind of techniques as eigenvalues and eigenvectors, and we'll talk a little bit about that in the 4th module. You can also use these things to decompose matrices, which enables you to do things like square matrices and take them to higher powers more easily. And again, these are things we will talk about in the 4th module. Eigenvalues are often used also for understanding centrality measures. When you say you have a network of individuals all connected to each other in some fashion, I hear networks are popular now. They're connected to each other in some fashion, and you can represent that connection, that set of connections via a matrix. We'll talk about that also in the 4th module. Well, sometimes you want to know certain properties of this network of connections. One property of interest is centrality, how central are individuals in the network. There are lots of different measures of centrality, but one prominent measure is called eigenvector centrality, and that kind of centrality uses eigenvalues and eigenvectors. Okay. So it's that way. The way we talk about it for the rest of this module is closely related to stochastic processes. Now, you can represent any kind of behavior in a dynamical system by either a system of differential equations in the continuous case or a system of difference equations in the discrete case. By discrete case here, we mean that these things happen in discrete time. So there's a period, something happens, the next period, and so on. So you might think of months or years or whatever. Discrete time processes are often more useful in social sciences and often actually biological sciences too, because you can, first of all, your data comes in discrete time. You don't have continuous data on the number of, say, troops at any moment. You measure troops at certain times, and you can figure the size of your army at any given, at a certain, maybe by year or by month or whatever. So you have discrete time data, not continuous time data, and you often conceptualize these things as continuous, as discrete time as well. If, say, you're dealing with, again, troop size for some kind of IR context, international relations context, you might want to understand troop sizes and how they change over time for military buildups. Well, they might not be changeable by the minute, right? They might be changeable only by some executive order or bill passed by Congress or so on. So you might want, or even by military fiat, but that might take time, meetings, and so on, and application of resources. So even then you have a discrete time action. So, it can, the number of armies you have can increase here or here or here or here, and so on. So discrete time processes are often pretty commonly used. It turns out we can represent changes in some state of the system say, the number of armies each of two states has by a matrix and a vector. So if a vector, we could call it a state vector, S, might be the number of armies in country 1 and the number of armies in country 2. And I'm sorry, I'm using A's again. I should use something else besides A's. Here, let's use capital R for armies, just because we're using A's for matrices a whole lot. Now, here's your, I'll write over that so it's still clearer. Now, if you want to know how these things change over time, you can apply a matrix to that. So here's a transition matrix, T, that when applied to some, and let's call this, put T's into these things, at some time T, it ends up being some state at time T plus 1. Well, this is a way of transitioning a system between the number of armies it has at time T and the number of armies each country has at time T plus 1. And if you keep applying this matrix over and over again, you can move the system along in a dynamical fashion. Right? And this is sort of a simple way of talking about dynamical systems. Dynamical systems are systems that change dynamically. They're not necessarily always stable. They move and they change over time according to some process. And for discrete time changes, you can often represent them, if there's a finite number of states, by a matrix. And the matrix can represent how you transition between states. So let's say these are all these are not stochastic. These are deterministic. Right? We call back our terms from part 3 of the class, probability. So we know exactly how they transition in this case. They're not stochastic processes. Well, they're degenerate ones, but they're deterministic. We know exactly how the state changes from time t to time t plus 1. And it changes according to this T, this capital T, this transition matrix. Now, we can sort of get at some of the properties of this matrix by understanding what happens to the characteristic states of this matrix, the characteristic vectors. If it's a characteristic vector, then we know if we applied some time t, the time t plus 1 vector would actually be a multiple of the time t vector, if that state vector were characteristic of the matrix. Well, what does lambda mean then? This is the eigenvalue corresponding to this eigenvector. Well, you can get a sense of how the system changes according to the values of the eigenvalues. And not too many values there. Right? So if the eigenvalue of this thing is greater than 1, then what's happening? Well, every time you apply the matrix T, you're effectively making the vector longer. So every single time you apply it, you make the vector longer and longer and longer. And the limit, as this thing goes to infinity, as you apply it an infinite number of times, the state vector explodes. Right? It gets infinitely long. So this is, in a sense, an explosive kind of dynamic behavior. If you keep applying the state vector, it explodes. If these things were armies, right, then you effectively get an explosive growth in military size. Now, of course, in real life, there's some kind of break on this growth, right? At some point, you run out of resources, right? But this can describe a sort of spiraling arms race where you keep constantly putting in more and more armies here. If you look at this as nuclear weapon growth, this is similar to an arms race model from Richardson in 1960. So this helps you understand that. Now, what if instead of being greater than 1, so if you have greater than 1, you have explosive growth. What if you were less than 1? Well, if you have less than 1, then your vector is getting smaller and smaller and smaller until eventually, in the limit, it approaches 0 length. So this is a contraction, right? This is a contraction. So rather than growth at all, you actually get contraction, eventually leading to no armies at all. Now again, there's probably some hard cutoff that people start, flip out if your armies go down to 0. So you probably wouldn't have, that'd be a movement not to have armies go to 0. Nevertheless, though, a dynamical system that had a lambda less than 1 would imply strong pressures to reduce the size of your army. Right? I might think of these kind of pressures as being prevalent after the Cold War between the U.S. and the USSR. Army sizes and overall militaries decreased because the pressures to increase size of armies significantly diminished with the splitting up of the Soviet Union. So that's another way of looking at dynamical systems, right? If the eigenvalues are less than 1, the system overall should be contracting. Now, if it's equal to 1, then you have a steady state. If it's equal to 1, you put in a state vector, and you get back the exact same state vector. So you have a steady state is called. A steady state is a state vector that's steady. It does not change over time with repeated applications of your transition matrix. It's an equilibrium of the system, right? It does not change with time. And this would be very interesting when we look at steady states of stochastic processes, of Markov processes, which we'll do in the next part of the class. But you can get a sense that if all the eigenvalues are either very big or very small or 1, you can learn something about how the state evolves over time. And this is yet another way in which eigenvalues and eigenvectors are used in understanding processes, dynamical processes. Now, you don't see a ton of dynamical processes in political science at the moment. There's been a movement away from these sort of deterministic difference models. These are all difference models, they're called. These are difference equations as opposed to differential equations, which deal with continuous versions of this. Nevertheless, this gives you a sense of how these things work. And just for reference, a differential equation might take a state and tell you that the change in state over time is equal to, if it was a constant, it could be this constant, right? So that's a differential equation. These are difference equations that tell you, that give you discrete changes over time. So that's it. This gives you a sense of where these things are used. And again, we'll go into more detail of the centrality measures, the use of eigenvalues and eigenvectors in centrality measures, and their use in principal components analysis in a later module. But this gives you a sense of a third use in differential equations, and difference equations, and dynamical systems. Okay. That's it. So the next 2 modules, we're going to look at how to actually calculate eigenvalues and eigenvectors with some examples. Thank you very much.